guys. Welcome everyone to the second online seminar of KAIS. And I give the word to Ahmed, which will give us a presentation.
Okay. So hello guys. I hope everyone is doing okay. I am Ahmed Emad from KTH. Today is our second seminar. Last time Ludovico talked about graph representation learning. Today I'm gonna extend the same topic to talk about context-aware graph representation learning. Before I start, there are two notes I would like to state. First, this is not my slide. This is a slide made by one of our research group member, but I thought it's really important today to talk about it. A second note that I'm still learning background, so I believe, I hope that I can answer all your questions. But guys, here you are more than welcome to help answer any question. So let's start. First, there are nowadays a massive amount of data that comes in a shape of graph. We have now social networks. We have medical network like interaction, protein-to-protein interactions. We have the internet itself and citation network, a lot of many application examples of data that we have already that motivates us to do a graph, what we call a graph analytics. Basically, now your data would be a graph. Given a graph, you apply techniques, including machine learning techniques, to come up with insights. And then perhaps these insights can be used further to change the graph itself, as in the task of link prediction. So what we need graph representation learning or network representation learning for, you can use it for tasks like classify or clarify nodes, give them labels in your graph. You can use it to predict missing links, predict true or false missing links in your graph. So these like a motivation. So let's talk now about graph representation learning briefly, and then move to talk about context-aware graph representation learning. We will cover two approaches, the splitter approach proposed by Google and graph neighborhood attentive pooling, which proposed by our postdoc, Zacharias. So context-free graph representation learning, it's you have a graph and you want to learn function, you have a graph G and you want to learn function F. So you learn a matrix. This matrix has dimensions of n, which is the number of nodes in the graph, times d, which is the dimension size that you pre-select before the training. So we have a matrix that you see now. Our purpose is to make this matrix representative for the graph, to convey the information that you explore from the graph. And we call this matrix embedding. So each row now corresponds to a node, and each node now has a vector or an embedding. So this is node embedding. That's this step we already done a graph representation learning. You can use it. You can use a resulting embedding with many tasks like link prediction or node classification, the tasks that we stated earlier. The learning objective of this function is, given a sample S of random walks, you traverse all the edges in each random walk, and you try to minimize the distance between your representation, your learned representation of the node of the edges, and the actual edge between U and V. So as you can see, this is a cross entropy. So typically it will have softmax output function. But the question here is a single embedding enough? I mean, is a single embedding of a node enough to represent a graph or represent nodes in the graph? Let's go through some applications and see and try to answer the question through these examples. In a Twitter, a normal active user on Twitter can be, for example, a data scientist. So that guy will be interested in the AI advances. He also can happen to be interested in other topics like global warming or philosophy. He has friends in KTH. So as you can see, an active user on Twitter can participate in many circles. Another example here, this is a real subgraph from Facebook. This is for a student. This guy has has friends, so neighbor nodes from high school. He happens to have friends from a company he's taking an internship in. He has friends or like peers from Stanford. That student happened to be in Stanford. So has students from Stanford who play basketball, another dimension, other peers from Stanford who play squash. So you can see these for one node, a student, one particular student, you can have 4 dimensions of data. This is another example. We can introduce like many examples, even with medical. On the left, the medical graph, you have drugs, and drugs can interact with many molecular different behavior functions. So now with this example, the question is it enough that you compress all this information about a node and put them in one vector? Our basic assumption is sometimes no. That's we're gonna, or the work I'm gonna talk about are gonna defend in the next slides. So what's that? That gets us to context-aware network representation learning. The task will change a little bit. So given a graph, you want to learn a function, but now we have a tensor, a multi-dimensional matrix. The dimensions are n, the number of nodes as before, times c, which is the number of contexts per node, times d, which is a pre-selected dimension size. So now we learn this multi-dimensional matrix. And then you apply different tasks, and you can find there are, from the literature actually, there are tasks like this, the third task here, the microscopic content prediction, that context-aware graph notation learning is kind of more fit for such task. It provides like better results. So now let's talk about the first technique of context-aware representation learning. We have a question here.
Can you please go where you explain the loss function and the random walk?
Okay.
Let's use only one microphone, but let's speak louder when we ask questions. Let's get closer.
So we'll go back a couple of slides. Okay.
Can you please go to the slide where you explain the loss function on the graph representation learning, and you say that you are integrating together a random walk?
This one?
Yes.
Okay.
So what are you minimizing here?
Your okay. Your input will be node U. Okay. Okay.
Okay.
And then you want to kind of predict node V, which is an actual neighbor that you have in your graph. Okay.
Okay.
So to predict that, you need to learn a matrix in between. That's the embedding you're learning. And your objective function, or your loss function, will try to see the distance between what you learn, like what the probability of predicting the node V and 1, which is like the actual probability of node V. Because like the ideal prediction, your gold standard would give 1 to node V, okay? And all the other nodes will have value 0. So you try to minimize the distance between the probability of your prediction of node V and 1, which is like the ultimate probability of node V.
And what's, because you have two loops, two summation, one going through O, which is observation, and S is what?
S is like a sample of random walks. So you thread many random walks in your graph, okay? And each random walks, of course, consists of a set of edges. So you have edge lists.
Okay.
Okay, so for each edge list, you you try to minimize the distance between U and V, which is like the corresponding or the surrounding nodes of that edge.
Okay, so you start with a, so S is like a
sample, the set of random walks. So O is a set of random walks, and O is a set of random walks, and for each random walk S, okay, you traverse over the edges in this random walk. Okay.
Okay, so these are two different loss functions actually. They are not associated with one another, right?
Which one?
And like the self-max and
No. Cross entropy loss function or loss function usually build on the output function that gives you probabilities. Then you compare this probability to the gold labels. Okay, P can be anything. In here, it's softmax.
And what is E?
I think maybe you can move these details to later and try to go with the main.
We can let's continue the slides and then we can have like this detailed question at the end.
So do you want us to stop in the middle or question to the end, because setting that might be.
Guys, if you have a question for clarification, yeah, you should ask me in the middle. But I mean, like detailed question, we can like make it to the end. Okay, so like guys can feel free to leave if they have like other commitments. Okay, so back to from where we stopped when we left. Okay, I believe we're here. Now we're talking about splitter, the first approach of a context-aware graph notation learning. It's proposed by Google, and we have an original graph. That graph has many 100 nodes, and it can happen to have many contexts, okay, overlapping clusters, I mean. The idea is to come up with what we call persona graph. Persona graph is just they transform the original graph to another graph which highlights the different context of nodes in the graph. And then they try to rewire the similar context of different nodes into one context. We will talk about that in the next slide. But given that we have a persona graph and original graph, if you apply graph notation learning on them and visualize the resulting embedding, we have these charts as you see on the right. Persona graph embedding show clustering behavior, which would like to say they are clustering according to their context, the nodes. So let's now go to how this splitter algorithm works actually, how they get the persona graph. Now we have this graph, this very small graph. This is our original graph, and we want our objective is to build a persona graph, GB. Okay. So first step is we will extract what we call an ego subgraph for each node. Ego subgraph for each node is the node itself and all the nodes that this node has a direct relationship with. So for node 1, you will have this ego subgraph, which happens to be the same as the original graph. For node 4 and 5, they will have the same ego subgraph because they only have 2 neighbors. And for node 2 and 3, they will have the same ego graph as you see now. So by this step, we now have an ego subgraph or ego network for each node in your graph. Second step is to apply a community detection algorithm on each of these ego subgraph. Okay, so it's like you are trying to extract the communities of each node, or let's say different context of each node. This we call it a microscopic community detection because we apply it on each node. Okay, so the scope is the node itself. So now for node 2 and 3, as you can see, we have on the left here, where's the mouse? Yeah, we have one community. Node 4 and 5, they have one community. Node 1, they happen to have 2 communities, the blue community, or let's say blue context, and the green community, which is like the green context. Okay. Step 3 is to start working on our persona graph. So first step is to create the persona nodes, like the nodes of the persona graph. How we do that? For each node from the original graph, you check how many communities or how many contexts they have from step 2, okay? And then you replicate this node as many times as the number of communities that it has. So for node 1, because we have two contexts, the blue context and the green context, we replicate that. So we have 2 nodes 1 in the transformer graph. So as you can see, that's why the algorithm, I think it's called the splitter. For the other nodes like 2 and 3, 4, 5, all of them has one context only, so they do not need to be replicated more than once. So we have only 1, 2, and 1, 3, one of each of the remaining nodes. Yes?
Yeah, so I'm just I have a question. So in the original graph, as we can see it, do we already declare the context? Like, for example, that 2, 3 represent the same context and 4 and 5 represent the same context?
No,
Because
no,
if I
no.
understand correctly, when you're extracting the ego subgraph, you are doing that based on the neighbors that each of the graph have. So, for example, if like, and when you are splitting the node number 1, you are splitting it based on the context or the number of, like, in a way, the number of neighbor it connects to.
Mhm.
So because you are splitting based on context, if you do not have prior information about what context each of these ego subgraphs hold, then how do you know whether to split like the node number 1? It can be that 2 and 3 and 4 and 5 represent the same context.
Yeah. Okay. I think according to the paper, you don't have to define a context before. The community detection algorithm will handle that for you. So they do not care if if the algorithm gives you 2 and 3 or gives you a different like division.
Mm-hmm.
It's about the structure itself, how the algorithm works. Okay. It
but-
just whatever the result is, dividing the ego network to
Mhm.
communities,
Mhm.
whatever communities is like, probably they will have some common structural
Okay.
features. So that's for him eventually lead to more of a
Mhm.
context sensitive graph.
All right. So I mean, it may occur that one is detected as a part of the whole,
Yes.
like
Yes.
a single
Yeah.
community. Okay.
I just labeled the community to context to like
To explain.
yeah, to explain to you guys to conceptually like deliver the idea.
Thank you.
Okay, thank you. So by step 3 now we have persona nodes for each of the for each of the nodes in the original graph. As you can see, ultimately you will have at least the same number of nodes from the original graph or more. Okay, depends depends on how many contexts you have per node. Here comes the last step, to add edges. So how to add edges? Let's take an example. We will have to go back to the original graph and traverse over all the edges that we have. So if we have example of an edge between node 1 and node 2 in the original graph, we will go to the ego networks from step 2, okay? And then we will try to check if node 2 lies in one of the in one of the communities of node 1, and if node 1 happens to be in the community, in one of the communities of node 2, like they need each of the nodes of the edge needs to lie in each other's community. So let's check that here. Node 1, let's start with node 1. Where's the mouse? Yeah. Node 1 here. We will see if node 2, okay. Yeah. We'll try to check if node 2 in one of its communities, and yes, you can see that node 2 lies in the green community of node 1. So let's call that a community 1. So node 2 lies in community 1. That would be, that will be equivalent to persona here, the persona 1 subscript 1. Let's switch and check the other condition about, let's check the ego subgraph of node 2 and check if node 1 lies actually in one of its communities. As you can see, it has one community already, and node 1 already lies in that community. So that means that both of nodes lies in each other's community, or lies in one of each other's contexts. That means that this context actually is one context. So we link them in the transformed persona graph that we have here. Okay. I hope everyone is following, right? So repeating this step, step number 4 for all the edges from the original graph, you end up with your persona graph. As you can see here, the number of edges must be eventually the same as the number of edges in the original graph, because like you only connect the same edge again from the original graph to the persona graph, but you now connect it to the replication, to the relevant context rather than the original node. So by now we ended the steps of the algorithm of the splitter approach. And now how they learn through two steps. Actually, the first step on the original graph, they apply a graph repetition learning technique on the original graph with the same learning function that we saw earlier. And then they apply a graph repetition learning technique on the extracted persona graph. Okay, so it's the same function, but here you iterate over the new edges. Okay. What's the link between these two steps, between these two functions? They initialize the node embedding of the persona graph here. They initialize with the embeddings that they have learned from the original graph. Okay, so they do not like randomly initialize the embedding of the nodes before doing the learning. They pre-initialize that with a pre-trained embedding from like the original graph. Okay, I will get to that later, why they did that. I will talk about that in the next slide maybe. That's a difference. Another difference is that they add a regularization term to their loss function. As you can see here, the regularization try to preserve the original structure, so they try to make sure that the embedding of the persona node UOP that you are trying to learn is still similar to the original node from the original graph. So you're preserving the original embedding. Okay. So it's like I think this is like a trick for the implementation, and this is their objective function. So they try to minimize this loss function that we have here. And as you can see now, this is the result of the embedding visualized to compare between Node2Vec on the right, on the left, sorry, and Splitter on the right. We have here three contexts. Okay, data mining on the left. We have information retrieval on the right above, and we have machine learning for graph on the right below. Okay. So according to there is I think you know who's Yuri Leskovich, of course. That guy has a contribution in machine learning for graph and for data mining. So it should be it should happens to be in two contexts. Okay. So according to Splitter, as you can see, this is actually happening. The Yuri Leskovich happens to be presented many times, like this is subcontext in the data mining context, and it happens to be actually presented in the machine learning for graph context. But if you check Node2Vec on the right, on the left, sorry, Yuri Leskovich only happened to be classified as data mining only. Okay. So that's the difference between using Node2Vec as a context-free graph implementation learning technique and using context-sensitive graph implementation learning technique. So now we're done talking about Splitter. We will talk about the next work in this domain. But let's highlight quickly on the issues of Splitter. First, Splitter rely on community detection, on explicit community detection. As we said earlier, you extract the egg network and then you apply a community detection on this network. Why is this an issue? Because you can have a node with high degree. I mean, it can happen that a node is connected to so many nodes, almost connected to the graph again. So you're just going back to square one. Another issue is a barrier training. As you saw, the Splitter requires two learning steps. So you need to go through two learning steps to do that. And why this is an issue, the barrier training is an issue particularly because when they do that, when they initialize the embedding of of persona nodes by the embedding from the original nodes, because the generated graph can have a problem, which you can have connected components. You can have a node which is isolated, a node that doesn't have any connection with any other node. So you cannot learn anything. You cannot learn anything about this node. You cannot learn an embedding for this node. And if you randomly initialize this node, so eventually we'll end up with like random embedding. So that's why they had to go through a two-step training. So our goal here is in this approach, in this graph neighborhood attentive pooling, in this work is to implicitly learn the context rather than try to explicitly model the context by doing a community detection on structure. Okay, so let's talk about this. Okay, two tips that we need to know that this work rely on. First, the attention mechanism tab. I believe all of you know what's the attention mechanism, but okay, attention mechanism is just simply try to bring attention to be more focused on the relevant features during the learning process. So let's take an example. So if you have a graph like this, okay, the same graph from before, and we will go through all the edges. Okay, so we start with edge 1 and 3, between node 1 and node 3. So this is like your first training example. You have an edge between node 1 and 3. And you could try to, you have many features. Actually, you can have features for 2, 4, 5 as like potential neighbors. But we want to bring more attention during learning on what feature, what of these nodes as features, what of these nodes are more important to the training example we have. In this case, between 1 and 3, what it seems to be a more relevant feature is 2. So because they have this neighbor in common. So we bring attention, we put attention, we highlight that more during the learning. We'll see how we do that later, of course. So for 1, 3, you will highlight 2 as an important feature, and you should consider that more while learning the embedding of 3 given 1, for example. And we ignore, of course, the other features. And then you do that with other edge like 1, 2, you have 3 as a feature to attend on, and you do that for 1, 5 edge and for the edge 1 and 4. As you can see, this is in a sense, implicitly covers the same context that the splitter example showed from before. So you have now attended 2 and 3 as a similar context, and 4 and 5 as similar context. Of course, this is like conceptually to illustrate the idea, but we will see how that actually works in their algorithm. Okay, but second, another tab that we need to know about is how they present their nodes in their work. Here, for each node, they will present it as a neighbor feature. Okay, neighbor feature, that means we will pre-select a size, fixed size will be 4, okay? And for each node, we will fill these 4 with 4 neighbors. So if a node happens to have more neighbors, that you will just prune them out, okay? But node 1, for example, have nodes 2, 3, 4, and 5. So it happens to have the same number of nodes as your sample size that you selected before. So okay, this is the neighbor feature, so neighbor feature vector for node 1. For node 2, because it has only 2 neighbors, 1 and 3. So you put them in the vector, and then you complete the rest of the vector with zeros. And you do that for all the nodes that you have in your graph. One more thing to pay attention to is consider the difference between node 1 and node 2. We have here node 3 in common, okay? So that means this is an in common neighbor, okay? That means it's something to attend or to pay attention to during learning, okay? So let's move forward. Let's talk about the original algorithm, because this work got inspired by the original algorithm, which is attentive pooling network. This algorithm was first presented in a graph in information retrieval, particularly in question answering task. It works like this: given a question Q, which has n number of words, you have a set of answers, possible answers, and you want to select the answer with the highest score relative to the question. So we just rank them, okay? How the algorithm actually works. We start here from top. We have a Q, which is a question represented as m number of words, and we have the candidate answer K, which is represented by n number of words. Both of them in parallel get through an embedding layer and then an LSTM layer, as you can see here. Okay. For who knows about LSTM, the output matrix of LSTM is a matrix that has dimension of D, which is the size, the hidden size that you set for your LSTM layer, times N or M, which is the input size. So so we have matrix Q. Matrix Q is matrix of D times M, which is the number of words in the question. So this is like a question matrix, and the same for answer matrix A. Next step is you combine between them through nonlinear function with stanch. This way of combining them, we call it weight interaction. Actually, when you use a matrix as a weight of the other matrix.
It's not combined with multiplication.
Yeah. It's not like combining, like I mean, it's interaction. I use combining to try to explain it better, but
no. But if you see the dimensions, it's like D multiplied by N.
Yeah, it's top product.
It's a matrix multiplication.
Yeah, this way of interaction, I try to join them. I say combine. I mean, to make it to like deliver the idea. Combine. I mean, try to join them. So you do that using weight interactions. I mean, you use one of the matrix as a weight of the other by multiplying the matrix. Okay. And to this step, you don't need to use the weight matrix U, but you can use it if you want to introduce more degree of freedom or maybe more expressive capacity to your model. But you can give up that, and I think your model will work just fine. Then the next layer, before we get to that, the output here will be G matrix. G matrix will be matrix of the dimensions M times N. Pay attention that M is the number of words in the question and in the number of words in the answer. Okay, so we have a matrix of question, the question and the answer. So next step here, this is the attention step. So if you check, if you look to the column, yeah, there's a question here.
What's the matrix U?
It's a weight matrix parameter. You introduce it to your model to handle to model how they should possibly interact with each other, the two matrices of A and Q.
So
we will,
if I can, in a sense, what you can think is that on the left you have this M times D. So for each of the M entries, you have D features. So you represent D different characteristics of your questions, and the D times N on the right, it represents D different features of the answers, of each answer. And now this D times D tells you how much each feature of the question relates to each feature of the answer. Because if you don't have it, you basically have a standard multiplication, each D with each D. But if you introduce this, you basically have this mixing where each of the D values on the left can go to influence each of the D values in the right. And this D times D tells you how much the concept of computer science influences the concept geography, for example. So it models these kind of interactions between the features.
Yes, exactly. So you can say it as more like alignment or interaction matrix, but again, you don't have to put this matrix in here. You can just give it away, and the matrix, like the matrix G, will learn during the backpropagation, and it will handle the interactions between A and Q in one matrix with the G. Okay. So now we have a G matrix. These matrices you can view it as the question and the answer, the words of the question, and how they relate to the words of the answer. And you have this step, which is the attention step. On the left, the column is pooling. Okay, I don't want to go through this. But in this step, you just trying to normalize the words of the question by their significance to the answer. Okay, simply they are doing that. If you have question about that, how it actually works, we can talk about that at the end. But you just normalize the matrix Q, which represents the question from this step. You normalize that by how they are important, by how, by which word is more important to the answer. So you highlighting the relevant features, the relevant words that you have of the question, okay? And you save that as a matrix, as a vector R. You do that too on the answer. So you choose to give more priority to the words of the answers that may be more relevant to the question, okay? Then you end up with two vectors. Yeah, is there a question here?
Yeah, so I just wanted to ask, like, maybe it's a very stupid question. So this particular process that you talked about, is it like a manual process during the training? Or how does it work? Like, how do you?
No, it's not.
Do you explicitly tell the model to highlight the important features for each?
Yeah, it's not manual. You do it. If you check the matrix here, okay, I didn't want to go.
Yeah, maybe like if you want to explain to the end, that's fine.
It just you select. Let's say now you select the word of the question sorry, which word of the question you want to have. Sorry, for each row that you have, each row corresponds to a word in the question. Okay, so for each row, you select one value. Okay, this is the maximum value, which is which word of the answer is like most important to that word of the question. Okay, you do that for all the words of the question, so you end up with a vector of words of
that is also learned.
Yeah, it's kind, yes, okay. Yes. So you have a vector for as it has the same length as the number of words in the question. Okay, then you softmax that, of course, to make it to get probabilities, and then you apply that. You apply Q by this resulting vector. So it's like you are saying which word actually has more priority according to which word in the answer, and the word that has more probability, of course, will keep more attention on the row, that row in the queue, that row equivalent to that word in the matrix Q. I know it's a lot of details, guys, but I didn't want to go through it. Okay, so we have this matrix R and R of Q, and we have another matrix which is R of AK. And the last step is to combine them, so you have a cosine similarity function that's your function that you want to maximize. You try to maximize the similarity between these two vectors. Okay, so this is if you don't get much about this model, it's fine. It's a kind of a mess model. And actually, this is very similar to my master's. Do you remember this slide presentation? Okay. Okay. So let's how the author now applies that architecture in their work on graph representational learning. The words become nodes, and the co-occurrence of words become an edge. So here we have node U, and we have node V. Okay, each node represented by the neighbor feature that you see here. Okay, let's remind ourselves that we only put neighbors of the neighbors of node U and the feature, and the other nodes we just put zeros for them. Okay, both of them will go through an embedding. That's the embedding that you try to learn, and you have U again like before, and you feed that through nonlinear. As you can see here, the author decided to give up the deep learning layer, the LSTM layer, because I believe their justification was this type of graph usually the order doesn't matter. So there was no point to apply a recurrent or LSTM layer. Okay, so they just fit that right away to the nonlinear function, the nonlinear layer that we have here, and then they apply the same attention mechanism from before. So they highlight only the nodes that are in common. Okay, these are what you bring attention to during the vector, and then you try to minimize the distance between both of them. Sorry. But as you can see here, they went for a hinge loss function, then a cosine similarity. Okay, There is no much difference between both of them, I believe. Just maybe hinge seems to be simpler than the cosine similarity, in essence.
The reason is because it's less sensitive to outliers.
Yeah, that could be a reason too. Yeah, good reason. Vankush here says because hinge could be more resilient to the outliers in your model, in your data. So maybe that's why they also decided to use a hinge loss function instead of the cosine similarity that we used before. That was the results of their prediction. Okay, the first 8 algorithm is context-free graph representation learning, and those two algorithms, CAN and DMTE, those context-aware models, and this is like their work hours. As you can see, their work outperform all the other works with less number of ages covered during learning. Okay, so by this we end our presentation. We want to say that if you want to use when to use context-aware learning, you need to explore your data first, see if there are potential contexts or not, and see what task you have in hand. See if the influence could be relevant to the task or not, and this could be your sign, your signal to use a context-aware learning or not. Okay, thank you. We are up now to any questions. Guys, are you still there?
Yeah, I mean, they are still online because...
Yes.
Yes, we are online.
Yes, we are.
We just don't have questions.
Yes, we're here.
One, if you allow me, I guess my question is for Ahmed and for Ludovico as well, because I'm not expert in this field. What is the difference between the network representation learning and the graph representation learning?
Okay, you can use them interchangeably. They basically the same. Network, you can see graph is just a mathematical representation of network.
Yes. So that's why, because for the last presentation it was on graph representation learning, and for this one in the beginning you introduced network representation learning. So yeah, basically, intuitively they are the same. Yeah. I thought that there are some differences since you didn't use the same terminology for both of them.
Yeah, thank you. We should have highlighted that earlier, but thank you. Good question.
Yeah, so if I can add something, it's basically a matter of a bit of the field where you apply it. So in some fields, it's more common to use the term network, while in other fields it's more common to use the term graph. But in the end, graph and network, in the context of representation learning, they are the same. So I would say, in general, in the context of representation learning, there is absolutely no difference between the two terms. It's just a marketing thing, we could say.
Thank you.
Okay.
I was going to add that maybe some data are intrinsically on network and some are not into a network structure, but you can construct a graph out of those data. So
maybe that's one way to view it.
I mean,
you say
when you have in signal processing, which I'm familiar with, and you have multiple sources of signals, and you want to do graph signal processing. The sources are not into some kind of intrinsic structure, but you
okay.
Start
So
to learn a network.
So you're saying that sometimes problem comes in naturally. It comes in a network structure like social networks, and sometimes the problem is not naturally represented network, but you just represent them in graph. You want to say that you try to find some structure. Okay, yeah, that should be right as well. Okay, so another question.
I have a question. Can you please go to the splitter and just go a bit briefly to the regularization term?
Okay.
What do you mean by that? Why you need to regularize?
The regularization term, what's regularization in general, or the
No,
term?
in that specific scenario, what you're trying to do with the
Okay.
observation and the...
Okay. Okay, let's go back to the learning slides, splitter learning slides. Okay, the question is what exactly does it mean does it mean to have regularization here? I think first let's go through the term. Here you try to predict the original embedding of node U, okay, from the original graph, given the node that you have that its equivalent is a persona graph, okay. Okay, so you try to minimize, in a sense, you try to minimize a distance between the U, which is like the original node in the graph, and its equivalent context node in the persona graph. So it's equivalent persona. Context means here persona. We can say persona, we can say context. So you try to minimize the persona node and the original node. Okay, by doing that, you're trying to make sure that you still not too far from the original embedding, because the original embedding reflected the original structure, and you don't want to get drifted away from that structure. Okay, that's one way to explain it. I think it could also happen during experiment. I mean, during implementation, you can end up with a scenario you don't have like much good results. So you try to come up with a trick that's very common actually in this kind of implementations. So you try to come up with a trick to see what may be a reason, then you try this kind of regularization and it gives you better results.
So in a sense, how you could see this is that because of the way the splitter graph, this persona graph is built, you're basically splitting a node into multiple personas, and this allows the communities that this node belongs into to move away from each other, because they are no longer bound by this single node that connects them. Because normally, if you have like node 1 in the middle, it will force the representations of 2 and 3 on one side and the representations of 4 and 5 on the other side to be not too far, because they are all anchored by node 1. The moment when you split node 1 into 2 subnodes, now these two communities don't have any more links in common, and so they could potentially move to the opposite sides of the spectrum. But it is true that this allows you to better distinguish them, but it also loses the fact that these two, in reality, they had a connection, which was node 1. This regularization term forces the two copies of node 1 to be themselves anchored to the original position of node 1, so that they can't drift too much from that, which means that the two communities, 2, 3, and 4, 5, will be able to move apart, but not completely in different areas. So it basically, you are, after you remove the link with them, now you want to put some kind of weak link so that you can keep the areas closed. For example, in the results about your Leskovich, you could see that when you apply splitter, your Leskovich ends up appearing in 2 clusters, but these 2 clusters are closer together than in the original one. So because Ure kind of connects them. So
yeah,
it helps with that.
Yeah, that's if you don't do that regularization term without this anchor, as Ludovico said, it would be like you are looking too much into context. So you lose a sense of the structure in the first place. Okay. Next question.
I have a very super quick question. If you can go to the hinge loss part, there is one term that I don't understand in it.
Okay. I'm sorry, too much animation. Okay, which one?
Yeah. The R minus at the end.
Actually, I don't remember the formula.
Should that be?
I think we can look that up. Okay, the question is, what are underscore? What this term is, but apparently I don't remember the formula, to be honest. So we are trying to find it, but maybe,
Modified version of.
but maybe we can do that later. We will make sure that we include that in the video, or maybe the slides.
It's like just another definition, I think.
It's what?
No, I was just checking hinge loss in Wikipedia, like one of the definitions.
It seems like kind of operation happens on R, but I'm not sure what kind of operations. It's like you're changing the you're affecting the vector of U by some operation happens between the other two vectors. But I don't know what underscore, what kind of operation is that? Okay, we can make that.
I will check it out.
Okay, we will find that later, and we will try to make sure that we have that on our slides at least. Okay, do we have any more questions?
Yes, one by me.
Okay.
In this slide again, why do we use specifically the tan function after the decomposition to produce the G graph?
The tanh function after the composition.
Yeah, why the specific one?
Okay, it's nonlinear functions. So to use the general idea of nonlinear functions is you try to model the embedding, but still you want to squash the values between certain range. For example, in tanh, you squash it between -1 and 1. Okay, so you try to represent the features through nonlinear function in a specific range, so you can calculate still the gradients for that curve, the curve of tanh. You got? Hello, you're still with me?
Yeah. Okay. Thanks.
I'm not sure that I answered like your question, but I think maybe someone can provide their answer here.
Yeah. So if you look at the loss function, you try to have on the right side of the max something smaller than 1 in order to have your training smooth, and that's why you need the loss function there to squeeze your output from into the -1 to 1.
Tanh function.
It's tangent, right?
Yeah.
So if you don't have that value there, then it's going to be a complete linear operation, and it's not going to generalize very well.
I think if I'm applying that model, I wouldn't have gone with tanh, because you have a loss function in a range from 0 to 1. So I would have gone with a better, like with a fit range, like maybe Relo instead of tanh.
I think yeah, you can.
Or
explain
yeah,
that
just
Okay.
one negative one. You can have a long spectrum with range. With range actually smaller range of your output.
But
So
wouldn't ReLU lose the ability to produce negative result, which means basically the fact that two things should not be together? ReLU can only represent positive relation between items, not negative relation. So that's why maybe TANH can provide a range that is symmetric around 0. Can say two things have to go together, or two things should not go together.
Yeah, I think like the
yeah, it's like you're putting more penalty on the things that should not be together. But in practically, you just in ReLU you just put them with 0. Somehow this doesn't change the result much as we think, as like theoretically we can't thread it.
I think like the Tajud is experimented with.
Yeah, actually, you can in most cases you can change the tangent with other activation functions, and you still have a comparable results.
Another thing, in the meantime, Susanna managed to look up that R minus, and it's the representation of a negative example, because you basically want to make U and V close to each other, and at the same time you pick another node that has nothing to do with you, and you put far away from you. So it's the concept of negative sampling, apparently, that they put there.
Okay.
It's minus V.
Yeah, it's
Minus V. Maybe it's missing.
yeah, it's okay. It should be R minus should be like, it's like the complementary version of vector V. It's like it's like the values or the values of vectors that you want to keep much distance as you can from that vector. So it's like the opposite of the contrast of V. Okay. So what's the question we had?
Well, I'm still puzzled with that tension, but I can.
Okay.
It's kind of like.
Okay, Sophia, are you still are you done with your question?
Yeah, thank you.
Okay, thank you.
I mean, to me, attention remains very difficult to understand.
But the point is that we could have an entire seminar about the use of attention in machine learning in general. It's a very wide topic, and it became very popular in recent years. So even many recent natural language processing models, they basically use only attention to do everything. So this is yeah, so it's very common.
There is a paper on that, which is attention is all you need.
Yeah.
And there's also a nice video on YouTube explaining that paper in comprehensible terms if you look up for that.
Yes. This paper, yeah, one of the papers, but it's really good papers. Attention is all you need. That's the name of the paper. And Susanna says it has a really nice video. So if you want, okay, we will post that. So if you want to learn more about attention, even me, I totally recommend to watch the video or read the paper. Okay, do we have any questions?
So
I think we're done.
If there are no more questions, then I think we can say thank you to Ahmed for his presentation.
Thank you.
Thank you guys.